All right, y'all, this is our last new topic before the summative. We will get a couple days of review in, but this is our last new topic in this unit. 1.7 notes, make sure you get it down in your notebook. IVT. 1.7 notes, intermediate value theorem. That is what we are writing down right now. 1.7 notes, intermediate value theorem. Okay, and the first part of this is going to be just like a little intro. So here's the intro. We're going to talk about continuous functions. So this is a little reminder about kind of what does a continuous function look like IRL, in real life. So this is Michael Jordan's height from like, I don't know, age 3 over here at 3'3". And then, you know, as he grows, he goes to 5'2", 5'7", 5'11", 6'3", 6'6". He stayed 6'6", and that's pretty much where he ended up. So this is Michael Jordan's height. In his sophomore year of high school, this is a prompt question for you. In his sophomore year of high school, Michael Jordan was 5'7", and in his senior year, he was 5'11". What height could we guess Michael was in his junior year? Go ahead and tell me a guess. What height do you think he could have been in his junior year of high school? Go. Okay. And hopefully we said anything, like you could have written any height between 5'7" and 5'11". Hopefully, 5'11". Hopefully you put any height in between those two heights. Why? Well, because that's how height works, right? Height, the function that is height, it's continuous. You have to meet the things in between. If you're 5'7" at some point, you have to hit all these heights in between, or we could like think of it as heights going up. You have to hit all these heights in between to get to 5'11". That means that you have a continuous function if you have to hit everything in between. Okay, so let's look at the graph of Michael Jordan's height. Now, this is just like random heights from birth to 55 years. It obviously doesn't have every single height. Do you think that it would be safe to say that we could connect these dots? Did he have to go from this first height down here? Actually, I do it in a different color. Did Michael have to go from this first height at birth to this height by hitting all the heights in between? Yes, of course he did. He can't just like jump an inch without hitting like all the little distances in between, right? So that means we could connect all these dots. We don't know exactly what it looks like in between, but we could connect all these dots. And then it looks like height levels off, which it should level off, right? Because like you stop growing eventually, and potentially maybe you even shrink when you get older. My dad has already started shrinking, so that could happen. Okay, so height is a continuous function. Let's like write this down. Height is a continuous function. And that's because you have to hit everything in between. That's what we're learning about right now. Like if you're continuous, you have to touch all of the heights or the y values in between as you go along the x-axis. Okay, so now let's talk about a different scenario. Michael was 6'6", his first and his last year with the Chicago Bulls. His height did not change. After he made it onto the Bulls, he did not grow. He was like a grown man. Okay, but there are other examples of real-life continuous functions that did change for Michael Jordan specifically between his first and last year with the Bulls. I want you to name some examples. Name some examples of other continuous functions that did change for Michael between his first and last year with the Bulls. I'm not going to tell you what changed. There's lots of examples, but I want you to name some. Go. Okay, so you know, we should I reviewed what y'all said, but like we could think of weight. Weight is continuous. If you go up in weight, you hit all the weights in between. If you go down in weight, you hit all the weights in between your end weight. That's one example. Age is another example. Y'all get the idea. There's certain things that you can't just skip. You can't just skip. That means we are continuous. You can't skip Y values. Okay, last little example. Last season's vans just went from $60, woohoo, to $30. Does that mean that sometime in the last year, the cost of those shoes equaled $45? So the vans went from 60 down to 30. Did they have to equal 45 at some point? Did they have to be something in between at some point? Yes or no? Explain. Okay, I would say no. And the reason why is just because something changes price doesn't mean it went to a price in the middle. Sometimes companies just make the decision to drop from 60 to 30 like that. They don't do anything in the middle. So I would say that price is not a continuous function. At least price of shoes. Price is not a continuous function. Okay, let's move on. So why are we talking about continuity? Why are we trying to visualize continuous functions? Because it's important for the intermediate value theorem. So write this down, intermediate value theorem. And you need to write the whole theorem down. Suppose f of x is continuous on a, b, and let m be any number between f of a and f of b. Then there exists at least one number c so that, okay, we're going to write two things down here. You can see that we're going to write two things down. But before we do that, let's just break this down a little bit. We have a little picture at the bottom, and I want to break down kind of some things on the picture. So, and the things in the theorem. So we have the interval AB. Let's look at the picture. Where do A and B show up? A is on my x-axis. B is also on my x-axis. So A and B have to be x values. So really quick, make sure you know A and B are x values. All right, and you should have written this whole theorem down. If you didn't already, make sure you're getting it down and you're almost done with that. Okay, let's find m. The theorem talks about m. Let's go to our graph. M is on the y-axis. It's just a y value. So let's go ahead and write that down for m. M is a y value. And then this always stumps kids. F of A and F of B. Okay, A is an x value, right? B is an x value. When you plug in x values to a function, when you plug the x values into the f function, you get y values. So these are y values. And you can see them here. F of A on your graph and F of B. Y values. Okay, cool. And then there exists at least one number C. Well, let's look at our graph. Where do we find C? There's three C's here. C1, C2, C3. They're all x values. So let's go ahead and write that down. C is an x value. Okay. So we've broken down what all these little things are. Now let's read this again. Suppose f is continuous, this function's continuous on AB on this x interval. Also, just so you know, those brackets, that's interval notation. And that means you were given two x values. You should know that for calculus. Two x's. Okay. So this function's continuous on this x interval. Let m be any number, just any y value, anything, between f of A and f of B. Then there's at least one number C such that, okay, and now let's write this theorem, finish the theorem off, such that A is less than or equal to C is less than or equal to B. And I want you to write a little note. This means C is in between A and B. That's how you write that in math language. See how C is in the middle right here? C is sitting in the middle. So C is in between A and B. All right, let's look at our graph. Are these C's in between A and B? Yes, they are. Okay, cool. So there's at least one C, so that C is in between A and B. And number 2, f of C equals M. Okay, f of C. Is that an x value or a y value? Put it in the box. F of C, x value or y value? All right, f of C, that should be an x or a y value. I'm so sorry. Y value. Why? Why is that a y value? Because C is an x, C is an x, but when you plug an x into a function, your output, your whole thing is a y. So this thing turns into a y value. So we have f of C equals m. That means this is the same as saying y equals m. All right, what is this theorem saying? Basically, look at this picture, and I would draw it if it helps, which it probably will. So draw a really quick sketch of it. It doesn't have to be perfect. But this theorem's saying if you have a continuous function, has to be continuous. This function is continuous. There's no holes, there's no jumps, there's no asymptotes. If you have a continuous function and you start with an interval A to B, you're looking from A to B, and then you pick a random y value. You pick a random y value that's in between the y values at x equals A and x equals B. So this is our random y value. At some point on your continuous function, you have to actually have a point at that y value. This one has 3. 3 y values equal m. At 3 x values, right? At 3 x values, we have 3 y values that are equal to m. Sometimes, though, you just have 1. This theorem is just saying you will always have at least 1. Okay, so now let's go down and do an example. Write this green example down, and then you don't have to write all of the pink, but it would be helpful if you can get it all. Let f of x equal x cubed minus x minus 1. Use the IVT. From now on, we're going to be calling the intermediate value theorem IVT. It's nice and short, to show that there is at least one solution for f of x equals 0 in the interval 1, 2. Okay, how to write an IVT answer proof to get AP credit. So the AP graders are, they're pretty strict, they're pretty hardcore, and they have expectations on y'all. So we're going to go through these expectations. The first thing you need to do is state or prove that the function is continuous. So we're here. State or prove that the function is continuous on the given interval. And how you know. Most of the time this is given. So really quick, let's go back to our question. Let f of x equal this thing. Use the IVT to show that at least one solution. Does it say anything about f of x being continuous? No, it does not give us that. But what type of function is f of x? It's x cubed is the highest power. That's a cubic. And cubics are continuous. So the first thing we have to do to get AP credit is state that the function is continuous. So this is how you do that. You say f of x is continuous on the interval, on the given interval. It says state that the function is continuous on the given interval, and how you know. So on the interval that we were given is, let me just highlight that. Here's my interval. Here's my function. Okay, so the interval is 1, 2. So we'll just copy that on 1, 2. Because, I'm going to say because it is a cubic. That's how we know. Okay, next step. Find the function value at each endpoint at f of a and f of b. We're trying to find the y. This is a y value. Find the y value at each endpoint. Okay, we're going to find f of a and f of b. So let's do it. F of a equals, all right, where do a and b come from? Let's go back to our theorem really quick. A and b are in the interval. That's a and b. So a here is 1. So we're going to first find f of 1, and then f of b is going to be equal to f of 2. All right, let's do that really quick. So f of 1 equals 1 cubed minus 1 minus 1 equals 1 minus 1, that's 0 minus 1 equals negative 1. All right, so f of a is negative 1. Now, if you want, you can like write that down. F of a equals negative 1. Sorry. Instead of a, let's put in 1 because that's what a is. So, and then f of 2 equals 2 cubed minus 2 minus 1. That's 8. Minus 2 is 6. Minus 1 is 5. F of 2 equals 5. Cool. We're done with step 2. Check. Find the function value at each endpoint. Now let's go to step 3. This is the weird part. This is the part that's kind of stressful for a lot of students. Use the following language to complete your proof. All right, AP is strict about how you write your answer. So we're going to like make sure that we almost kind of memorize how to write our answer. Here we go. You're going to write this every time. Like this is your conclusion. Since f of x is continuous on the interval 1, 2, the IVT applies. All right, that's where we're going to start. Now, before we move to the next part, we need to talk about what this means, like graphically. We're just going to very quickly go over this. So we have this function, this cubic function, and we have the values a equals 1. And then I would like for you to draw this because this will help you understand what we're doing. B equals 2, right? That's our interval, 1 to 2. And we have points that we found. We found that f of 1 is, oops, I should have gone down here. That's okay. We'll say f of 1 is negative 1. Negative 1. That's f of 1 because this is x equals 1, right? F of 2 is 5. My bad. Deleted that. Okay, f of 2 is 5. So let's go ahead and put a 5 on our graph. And here's that value. Our function's continuous. We know that because it's a cubic. So what that means, just like Michael Jordan's height, these dots have to connect at some point. So let's go ahead and connect the dots. We don't know what shape the function is, but it has to connect. Okay, and what we're trying to prove is, let's look at what we're trying to prove. What are we even trying to prove? Show that there is at least one solution for f of x equals 0. That's saying for y equals 0. Does that have to be true? Let's check. Look at your graph that we just did. Doesn't y have to equal 0? At some point in between x equals a and x equals b, y has to equal 0 because our function's continuous. That's all we're doing, is we're saying, oh, we have a lower bound. We have a number that is below 0 for a y value, negative 1. We have a number that is above 0 for a y value, 5. So at some point, it has to equal 0 on its way from negative 1 to 5. Okay, so now let's go back to like finishing to get full AP credit for this proof. Since f of x is continuous on 1, 2, the IVT applies. Since, now we're going to write because we're going to say 0 is in between 1 and 2. Or sorry, negative 1, use your y values, and 5. Since 0 is in between negative 1, oops, I'm going to use less than. Less than 0 is less than 5. That's saying since 0 is in between negative 1 and 5. That's how you say it in math. Because 0 is in the middle, by the IVT, there must be at least one x value, we're going to say C, on AB. There has to be some x value. C would happen right here on our graph. We don't know what the x value is, but we know there is one x value in between a and b such that, and then you finally conclude f of x equals 0. Go back to what it was asking you. That has to be true. All right, I know this seems like a lot and it's kind of confusing. And with practice, you get stronger at it. This is guaranteed going to show up on the AP exam. Guaranteed. So what I want you to do now is I want you to try. And we're going to go to this problem. Use the steps that you wrote in your note and then use the little green like wording above to try this problem on your own. And then we're going to see if you got it right. Go. Okay, I'm going to do this one. So we're going to look at step 1. Step 1 says state or prove that the function's continuous on the given interval. And how you know. We're going to start with this first sentence. So I'm going to say since, actually, yeah, I'll go ahead and start my first sentence for like my final answer. Since f of x is continuous on the interval, now we have our interval in different notation, but you could be written like this as well. Since f of x is continuous on 0, 5, and then I'm just going to squeeze in here, how do I know? Because it's cubic. It's also a cubic. Okay, and then we're going to go to the next part. We need to find, step 2, find the function y values at each endpoint. So I'm going to like go down here and do that, and then I'll finish my final answer. F of 0, I need to find f of 0 and f of 5, because those are our two endpoints. F of 0 is going to be 0 cubed, minus 5 times 0 squared plus 8 times 0 minus 9. That equals -9. And then f of 5 is going to be a big number because it has 5 cubed. So let's see what f of 5 ends up being. Oh, G. Oh my gosh, y'all. Oh my gosh. Hold on. Okay. Let me show y'all really, really big mistake. AP graders hate this. They will not give you credit, actually. We started with G. I wrote F. You do that on the AP exam, you don't get credit. You have two options. If you mess up like I do, you have two options. One, you can go back and erase everything and write G of X instead. Or if you're like, oh my gosh, I've written f of x too many times and I don't want to go back and change all of the f of x's to g of x, you can just write on the problem somewhere on your paper, you can write let g of x equal f of x. That's telling the AP graders, hey, I'm going to start calling g of x f of x, and you're allowed to keep going. So I'm going to do that because I don't want to erase all my f's. Okay, and I got f of 5 equals 31. Okay, so now we're going to go to step 2. We found both of those function values. We can write the next piece of our answer right here. Since, what are we trying to find? We're trying to find g of c equals 27. So we're going to say since 27 is in between -9 and 31. That's true. So since -9 is less than 27's in the middle, since that's true, let's go back to our little green thing so we make sure we use all the right language. Since that is true, by the IVT, you are allowed to abbreviate intermediate value theorem. There must be at least one x value c, they called it c here, right? X value c on, oh no, I wrote AB here on the example, and I meant to write my interval, 1, 2. So we're going to, instead of AB, we're going to write our actual interval, 0, 5. There has to be some c in between 0 and 5, such that, and we finish it off by writing what they were asking us to prove, such that f, I wrote f instead of g, remember, f of c equals 27. Because I decided, hey, how about let's start calling g's f's. So if you make that mistake, remember, you can always write that, or you can go back and change all your f's back to g's. Okay, this is the answer. That is your answer to that proof. Now we're going to do a couple practice problems. Good work.